Okay, these are some more problems on section 9.4. These are kind of continuation of what we were doing. Exercises 7 through 22 says find the radius of convergence of the power series. And number 11, this was our power series here. Now, you could write this, and I didn't do that, but you could have written this as x minus 2 all over 10 to the nth power. So you could see that that's a geometric series, and that's your ratio. So we know a geometric series converges whenever r is, the absolute value of r is less than 1. So basically we have this x minus 2 over 10 is less than 1. Now remember from our definition, it has to be x minus a in that form, not x minus a over 10. So we have to get rid of the fraction, so we multiply both sides by 10, and there's your radius of convergence. Now we're not going to talk about the interval of convergence until we can talk about the endpoints. But please remember, and I talked about that before, if you go back and refer to that theorem 5, it's always x minus a is less than r. And again, look at theorem 5 a lot, because you really need to understand that thoroughly. Okay, let's take a look at number 12. And if I go through these fast, and I know this is kind of tight, you can always just freeze it and pause it and take a look at it. So this was the series, and this wasn't a geometric series. We always look for a geometric series because that's the easiest, because we know what's happening. We don't even need to worry about the endpoints because it's always open. So this is going to be n x to the n over n plus 2. So we're going to use the ratio test. And in order to take care of any possibility of negative signs, we always take the absolute value and shoot for absolute convergence. And remember, if it converges absolutely, it converges. So this is kind of a safe way to go. And we're going to use the ratio test. So that's going to be the limit of the absolute value of a sub n plus 1 over a sub n. And then we can just take this, this would be a sub n plus 1, and multiply it by the reciprocal of a sub n. And that's what this is over here. This is the reciprocal, n plus 2 over n times, and then the absolute value of x to the n. Now, we don't have to worry about absolute value on the n plus 2 because n is going to be going from 0 to infinity, so it's going to be positive. So n or n plus 2 will be positive, so we don't need the absolute value there. Now, for the n plus 1, remember, the a sub n plus 1, every time you see an n, you put an n plus 1. Every time you see an n, you put an n plus 1. And this is n plus 1 plus 2 is n plus 3. So this is the a sub n, and this is divided by this or multiplied by the reciprocal. And we just multiply by the reciprocal because it saves a lot of space. Okay? All right, now, we could take this and we can rewrite this as the n plus 1 that we don't have to rewrite, but we can rewrite this as x to the n, and this is all going to be the absolute value, plus x to the first, right? If we multiply these, you just add the exponents. So n plus 1 is x to the n plus 1. The absolute value stays the same. And the reason why we did that is because we have an x to the n down here, so we can cancel those or change those to be 1. Okay? So what's left now is the n plus 1, n plus 2 all over n plus 3, and then times the absolute value of x over here. This is all that's left. Now, as n approaches infinity, we have to use some of our little limit tricks that we learned. We talked about these before. Now, as n approaches infinity, the 1 becomes so insignificant that we can just forget it. We could forget that 2, and we could forget the 3, and we could think of this as n times n over n times n, which is just 1. Another way you could do it if you wanted to is you could multiply this out, and you'd have 1n squared, and then the rest of the trinomial. If you multiply this out, you'd have 1x squared plus 3n. And again, you could look at the highest degree terms, which would be n squares, and their coefficients would be 1, so we'd have 1 over 1, which would still be 1. We take the ratio of the highest degree terms, like we do for horizontal asymptotes. So there's all kinds of ways to do that. Either way, this limit will be 1. So I just have 1 times the absolute value of x. Now, that's going to be my L. Now, by the ratio test, the series, or by the ratio test, I should say, by the ratio test, we know the series converges when L is less than 1. So this is L, so it converges whenever the absolute value of x is less than 1. So my radius of convergence is 1. Okay. So if that makes sense. And you can take a look at that. I think I put enough steps there, so it makes sense. So this was just taking the limit as it approaches infinity. But there's lots of ways to do that. Okay, number 13. Okay, the ratio test is this is what we're going to do on this one also. It's not a geometric series. So again, this is going to be my n plus 1 term, and this is going to be the reciprocal. So you see the absolute value of the x to the n of the bottom, and you see the n times the square root of n, and 3 to the n. Okay? That's going to be the limit of this whole thing as n approaches infinity. Maybe could have put a little parentheses around there so you realize that limits on the whole thing. Okay? All right, so what have we got here? So I kind of went ahead, I kind of skipped some steps. In other words, I said this is n plus 1, and this is n, so those n's cancel, so that just leaves me with 1 x to the n. So what, I'm sorry, 1 absolute value of x. So this n, x to the n, cancels with that x to the n, just leaves me with x to the first power. So if you follow that, and then, again, when I write it, I better go over this. This is x to the n plus 1. This is n plus 1, the square root of n plus 1, and 3 to the n plus 1. Every time we see an n, we put the n plus 1. All right? That's what this part is. Every time you see an n, you put an n plus 1. And so this times the reciprocal. And then again, now I can cancel, as I said, so I just have this absolute value of the n. And then I have all this stuff on the top. Now, this is 3 to the n, and this is 3 to the n plus 1, so I'm going to do the same thing like I did with the x. 3 to the n, and remember when you're dividing, you just subtract the exponents. If I take, well, either way, because I leave it on the bottom, I've got 3 to the n plus 1. N plus 1 minus n is just 1, either way. So 3 to the n cancels with 3, and then just leaves me with 3 to the 1, or 3. So that's why I just have a 3 on the bottom. So these become 3. Hope you can see that. Okay. And then I have the n, square root of n, and I've got n plus 1 and the square root of n plus 1. Okay? So I still have the 3 over here. I put the absolute value of x out in front so I can figure out this limit. I want to figure out this limit now. Now again, as n goes to infinity, we can get rid of these little 1s here. So I've got n, or square root of n. This becomes n and square root of n. As n becomes very, very large, the 1s are insignificant, so they'll go away. And we have n over n is 1, square root of n over square root of n is 1, so I just have 1/3. So I end up with all this limit ending up being 1/3 absolute value of x. And that's going to be my L. That's the limit as n approaches infinity. So if you guys can follow all that, you can follow this stuff here. All these cancel, and those cancel. They cancel the same way. Okay? So L equals the absolute value of x over 3, and this converges when L is less than 1. If you go back and look at your ratio test, it says it converges when L is less than 1. So when this is less than 1, it converges, and we want to get rid of the 3, so we multiply both sides by 3, and so that's my radius of convergence, 3. The absolute value of x is less than 3. That's all set up in the form we want, x minus a. In this case, a is 0. We're set. Okay, so if that makes sense. And if you have any questions on these steps, please ask in class, and I can write out, I can expand them a little bit.